Now we're going to go more in detail about the Somatic SNF and Indel discovery. So Lee presented the overview of overall somatic pipelines that GATK has. Now we'll talk about actual tools inside of the Somatic SNF and Indel workflow. So this is what it looks like. So what is the problem we're trying to solve here? We're trying to call events that occur in a cancer sample, samples that are very heterogeneous by nature, and also that has possible normal contamination. Therefore, the events that occur there are occurring at a very low allele fraction. And if we also consider the fact that we have a vastly overwhelming majority of artifacts, then calling those very low allele fraction events becomes very hard. And therefore, a lot of the workflow is filtering, because we need to be able to get rid of a lot of false positives that will come up when we try to call those allele fraction events. So basically, the middle part, of the actual diagram is the mutex tool itself. It takes a tumor normal pair and also the panel of normals that Lee talked about. And then everything else, including the stuff on the side, is part of the filtering. So one thing to say is that this tool is changing very rapidly. In fact, we had to update this particular diagram just for this workshop, and it will continue to change as far as I know. So always look in the forum for the newest and greatest. Yeah? What is what? Sorry. This is the general population. So it's just allele frequency in the general population. So for example, nomad. Right. So we have a problem of having very low signal to noise ratio, because overwhelming number of our events that we will see in a somatic sample will be actually coming from germline, like about 1,000 to 1. So we really have to be careful about not calling those. And in fact, the number of artifacts that will come from sequencing, misread bases, misaligned reads, and things like that will be also an overwhelming majority of our signal. And we also need to be able to filter those out in order to not have most of our called variants be actually artifacts. So how do we do that in this workflow? So as Lee already showed you in his presentation, since we have a normal sample, we are able to see which events we have in common, and we just disregard those. And if we don't have an event in a normal, but we seem to have some kind of activity in the tumor, then we will look closely at that particular site. So this is how we subtract out the signal that comes from the normal sample. Now, one of the more powerful thing that we have now for filtering out false positive in the mutex workflow is what we call panel of normals, which is basically a VCF of calls that were made by calling mutex on a set of normal samples. And if that event pop out more than twice, then we put it in this VCF. And if we see it in our tumor sample, we just ignore it. And the main purpose of that is filtering out the recurring technical artifacts. And you should be constructing that panel of normals from the samples that came from roughly the same sequencing design. It also helps to run the workflow on the samples that we don't have a matched normal for. So we can run the tool in tumor-only mode, and then we can provide panel of normals and also the population allele frequencies to be able to get rid of the possible germline signal.
When you mention population allele frequencies, that's sort of like using the DBSNP database, or
Nomad.
Okay.
Yeah.
Like recurrent SNPs in the population.
Yeah, exactly. Well, so basically, it's a file that it's a site-only VCF that has the sites with their particular allele frequency in the info field. Okay, the first part of the workflow is where the calling happens. That actually outputs a raw VCF with unfiltered variants. And here we kind of assume that all the reads are independent. So for example, if we see 3 reads that support a certain variant, we will be likely to say that it's probably a real variant because we have 3 independent sources of information, so we'll call it. But in a later filtering step, we will be it'll be less naive, and we will, for example, say, oh, well, all of those actually show that variant comes from the same strand, for example, or it comes from one end of the read, and so we'll filter it out. The guts of the mutex2 actually resemble to those of haplotype caller. In fact, we use a lot of the same machinery. And the process is also similar. So we start by identifying the active regions, where we go through each particular site, and we look at the pileups on those sites, and we try to see where there are possible events that occur in a tumor sample. And if the site isn't PON, then we exclude it. And if the site looks like it has an event in a normal, we also toss it out. Then we take all the reads from the normal and the tumor, and we filter them out. And we filter out the reads in a tumor much more stringently than those in a normal sample by things like mapping quality, for example. And then we toss those reads into assembler. So you put them, camerize them, put them in a De Bruijn graph. We assemble most likely haplotypes. Then we calculate this big read by haplotype per read likelihood matrix. And then we use that matrix to actually determine our most likely alleles. So this is basically kind of very similar to what haplotype caller does. So yeah, it mentions here in the slide that we also have allele-specific calling, meaning that we will use the information from the germline population frequencies resource to basically inform our prior about the probability that an event exists in a germline sample at that particular site. So this is an example of when the machinery of the haplotype caller helps us a lot in determining indels. So this is an example of a particular event where we we have an 120 base pair deletion, and when we align the reads to the reference, we can see, so everything in gray matches the reference exactly, and then we have a lot of mismatches at some ends of those reads. And in fact, if we look at the reference closely, we can see that these reads map somewhere, these bases map somewhere over here, and these bases map somewhere over there, but the aligner does not have that power to actually know that because it doesn't look or assemble things locally, but we can do that using a haplotype caller, and we get this. So we get very nice alignment out of that, and we see that there's, in fact, a 120 base pair deletion. So a little bit about the very last step of that diagram from 2 slides before, about actually finding which alleles we have at any particular site. So this is just a general kind of idea of how we compute it. So we have a model for a reference allele, and we have a model that we have both reference and out allele at any particular site, and we compute those likelihoods. We find the log likelihoods ratio, and then we have a magic constant to say whether we will call that site, whether we will emit it, or we won't. And right now, I think that magic constant is 5.3, but in fact, because the tool is changing so rapidly, that magic constant is going to go away or already went away in the very latest release, and the things that are in a smarter way. So this is one example of such positive changes that we have in Mutex 2. So this is basically trying to do the same things as the last slide described, but in a more rigorous way, where we have a nice Bayesian model for modeling which alleles the reads came from, where R is our observed reads, and then Z is a Leiden variable that says this read came from which allele, and F is actually a random variable for allele fraction, which basically says that, well, we know what allele fraction is, but we don't necessarily know that that allele fraction represents the actual fraction of the cells in the population. So we model that through this random variable F, and then we marginalize it out, and this gives us a power to call, a nice way to call multi-allelic sites. So we can call, we can be able to compute this log likelihood ratio for multiple alleles. Okay, are there any questions so far about the first part of the mutex? Okay, so the second part is filtering. And here we take the entire VCF output of the variance that we called in the mutex, in the output of mutex, and we do we run some other tools to compute things like, for example, contamination, and then we put it all in one filtering tool that will output the final VCF. So the way that it's done right now in the workflow is a lot of metrics are computed in the mutex 2 step, and those metrics are actually going to be part of the VCF that is output by the mutex 2 tool. And for example, there will be a metric that indicates coverage at a particular site, or read position, or average read positions, things like that. And all of these things will go in the VCF as attributes for any site, and then this VCF will be passed to the filtering tool, which will look at those attributes, and it will define some hard filters for filtering those events. For example, one of such hard filters is filtering on multi-allelic sites, where we say if there's more than 3 alleles, it's probably garbage and we toss it out. We also look at the read position, where we say if the variant occurs at the very end of every read, it's also probably garbage, we toss it out. We also have some slightly more elaborate filters for which we have we also written probabilistic models to capture those particular biases in the data. For example, one of these is orientation bias, and that was the very first pre-processing part of the workflow. We will also touch upon it a little bit later. This, for example, is very important for calling FFPE samples, if you're dealing with that. Okay, so another thing is contamination. Because we want to call things that occur at a very low allele fraction, contamination by other samples can severely affect that. So we want to be able to have some kind of estimate on that. So we have a new tool in GATK4 that does it, that's similar to the previous tool called Contest. The idea is basically it looks at the home large sites and tries to estimate the contamination level based on that. It also works, yes?
Does this new algorithm require a match normal?
So it does not. It will work probably better if you do have a match normal, but it's still able to work very well with a set of very smart things without. So yeah, match normal is optional. Okay, actually, are there any questions before we go to the command lines? Okay, so there's nothing I wanted to say in particular about the CLIs. So this is a part of the pre-processing. We call this collect F1 R2 counts tool that will collect the number of counts in the forward and backward reads, and then we put output of that to the read orientation model tool, and that will be passed to mutex tool. There's actually not a great reason for that not to be passed directly into the filtering tool, and that actually might change later. So now, given the output of the orientation bias model, now we call the mutex2. One thing to mention here is, one thing that changed recently is that we don't have to specify the name of the tumor sample. We just specify the sample itself, and then we specify the normal and the name of the normal. And then we can optionally provide the population allele frequencies, resource, and panel of normals. So this is pre-processing for the contamination tool. We call it a normal. We have a smaller resource for population allele frequencies. which is in our resource bucket. And we use that in this case. We also call it a normal, and then we pass both outputs to the calculate contamination. We get the contamination table output that we will pass to the filter mutex call. And the output of that will be the very, very final VCF. And that's it.
So slides 11, you were saying at low coverage sites, GATK4 perform better than GATK3. I was wondering, like, how much it performs if you have like benchmarks to
Are you
be able to like know if
Are you talking about this slide?
11.
I'm sorry?
The 11th one?
Yeah, that's that
Oh
one.
yeah.
Oh, yeah. So this just says that it performs better at low coverage size because we marginalized out this F. It does not necessarily say that it outperforms GATK3, but it actually does. I don't have the performance. Yeah.
You don't mind me jumping in?
No, go ahead.
Okay, so here's the deal. GATK3 M2 has worse performance than GATK4 M2 in every regard, including price. Okay, I do not have a benchmark for that specific change, okay? But there's probably one somewhere that we can dust off from years ago. There really is no reason to use like a GATK3 M2. And by the way, if you ask questions about it on the forum, we're just going to say upgrade. Does that answer your question?
Yes, I think so. It's because we're using house-made like tools, like pipelines, because GATK3 was not, in some aspects, better than what we're using, and get confirmed. So yeah, now we have to like evaluate if GATK4 is better than our own house-made tools. So that's why I think asking.
Oh, so you made tools based on, so for everyone who is in here, GATK is not just a collection of tools, it's also a framework so that you can write your own tools. So it sounds like you wrote your own tools, and now you are trying to evaluate whether upgrading to GATK4 will be a good idea for your tools. So from a developer standpoint, GATK4 is much easier to deal with. I admit, though, that I've only ever written like one tool with GATK3, and it was a long time ago, and I'm much more familiar with GATK4. In other words, what I'm saying is I am biased. But if you want help, we're not going to support like developing new tools on GATK3. I mean, you can ask questions and maybe someone will be nice. Whereas if you ask about developing new tools on GATK4, we will be more than happy to help you.